can you solve the 6 calculus problems on the second week of the Calculus 6? It's just under 2 months to the first A-level maths exams. So doing these problems are going to really build up these essential skills that you need for the exam. So if you want to pause the video here, and solutions going through how you work these out will follow shortly. So here we have a function divided by another function. Now, when I have this scenario and I can't simplify it any further, what I want to do is use the quotient rule. So I'm going to let u be e to the 7x and v be sine x. And then what I'm going to do is find du by dx and dv by dx. So the quotient rule is something that is given to you in your A-level formula book. So you can use this result, unlike product rule, which isn't given to you in the exam. That one you need to remember yourself. So for the quotient rule, what you have to do is v times du by dx, so the second function, or the function on the bottom of your fraction, times the derivative of the function on the top of the fraction. So we do v times du by dx, and we take away dv by dx times by u. All of that gets divided by v squared. So here's how this looks. So timesing the du by dx by the v first. And then we're subtracting u times dv by dx. Make sure that you're taking these away. Finally, we're going to divide it all by v squared. So we're going to divide it all by sine squared. Okay, and that's it. You can do some more. You can factor out an e to the 7x. For example, sine squared, you could write that as cosec squared if you didn't want the fraction, I guess. So there'll be some other things you could do with it, but I think sometimes in exams, if they haven't asked for a particular form, you usually find just leave it like that. And sometimes the question anyway, you're going to find a stationary point, so you're going to set it to 0. So you don't need to go too hard on the simplifying if you haven't been asked to leave it in a particular form, because often we are going to just set it to 0 or substitute some more numbers in anyway. Right then, question number 2. So this time we've got some parametric equations. We've got x equals cos 2t and y equals sec t. So when we have parametric equations, you could try and come up with the Cartesian equation, so just an equation in terms of y and x, and then just find dy by dx like that. But usually it's going to be far easier to just find dx by dt and dy by dt. So then to find dy by dx, you just do dy by dt divided by dx by dt. So let's see how this looks. So the key equation here, or the key formula, is going to be dy by dx is dy by dt divided by dx by dt. So we need to find dx by dt and dy by dt, so let's do that. So dx by dt, we're going to differentiate cos 2t with respect to t. So that becomes minus 2 sine 2t. Okay, so because there's the coefficient of t, there's a 2, times by 2. When we differentiate cos, it goes to minus sine. And then when we differentiate sec t, okay, we get the following result, which is just going to be sec tan. So then, as we said before, dy by dx, just dy by dt divided by dx by dt. So we're just dividing dy by dt by dx by dt and that's our dy by dx. So yeah, again, I'm just going to leave it like that, but you could yet again simplify that further. As a little sort of extra exercise, I'll leave it to you if you want to try and see if you can prove that actually this can just be written as a single trig function. And you can do that by using some double angle formulae, just trying to get everything in terms of sine and cos, and you should end up getting minus a half sec cubed t. But I'll leave that as a little extension. If you want me to kind of go through that, let me know in the comments. Okay, then question number 3. So we are going to differentiate 5 to the power of 2x. So I'm going to use the chain rule to approach this one. What I'm going to do is this power of 2x, I'm going to call that u to make this a little bit easier. Might be longer, but we're kind of breaking it down into smaller steps doing it this way. So y will be 5 to the power of u, where u is 2x. Now we're going to talk about an important result that we need to know and we need to be able to apply in our exam. It's not one that's given in the formula book, and that's the derivative of 5 to the power of u. Now if you go back through notes or look in textbooks, the proof will be there how you get this result. But when you have something in general that's a to the power of x, when you differentiate that, that's a to the power of x times the natural logarithm of a. Okay, so if you differentiate a to the power of x, where a is a constant, the result is when you differentiate it, a to the power of x times natural log of a. You need to know this, it's not in the formula book, so go back and look through your notes if you are unsure of this. So applying it for our problem here, when we differentiate 5 to the power of u, what's going to happen is we just write the 5 to the power of u, but then you're going to times that by natural log of 5. And then finally we need to find du by dx as part of this. And then because it's chain rule, I can find dy by dx by doing dy by du times by du by dx. So just timesing the two things I've just found together there. And I get this result of 2 natural log of 5 times 5 to the power of u. Or if you like, you could, instead of writing it as 2 natural log 5, you could write it as natural log of 25 using your laws of logarithms. So quite a quick one, that one, but I think sometimes students forget about how to differentiate functions in the form a to the power of x. So I wanted to throw that one in there. Okay, on to the integration now, and looking at this question, we're integrating a fraction here with a function on top and a function on bottom. Now, the first thing to look at is, can I simplify it? And there's nothing that immediately jumps out that we can simplify. But what we can notice is, well, what happens if I differentiate my denominator? And you can see in this case, if we differentiate 3 plus 2 cos x, when you differentiate the 3, that goes to 0, and differentiate 2 cos x, well, that's going to go to minus 2 sin x. So if we differentiate our denominator, we end up with a result that is a multiple of the numerator. And in those cases, I should be thinking that the result is going to take the form of natural log of a function. So what we're going to do is we're going to try and see what happens if I were to differentiate natural log of 3 plus 2 cos x. Okay, so natural log of what is on my denominator. So let's see what happens. Okay, and if in doubt, you can check this via the chain rule, but the quick way of differentiating natural log of a function is that when you differentiate it, the function within the modulus there goes on your denominator, as so. And on the numerator goes the derivative of the denominator. So differentiate 3 plus 2 cos x. That gives us minus 2 sine x. So we almost get what we started out with here, what we were trying to integrate with in the first place. So what I'm doing there is I'm differentiating to see, well, if that was the answer, if I differentiated it back, do I get what I started with? Almost, but not quite. So we're going to need to adjust our coefficient of natural log here to compensate for this. So the answer is almost natural log of 3 plus 2 cos x plus c, of course. But if I were to differentiate that, I'd end up with a minus 2 on the top. So I don't want this minus 2. So therefore, I'm going to need to multiply this by negative a half. And if you were to differentiate this back, then you'll get sine x over 3 plus 2 cos x. Okay, on to question 5 then. Okay, so we've got here 4 sine 8x cos 8x. Now, you have got a function times a function, but we certainly don't want to be going for integration by parts here. That would be just way too long of a process, and there's a much simpler way that we can do this. Now, whenever we see sine of an angle times cos of an angle, that should have alarm bells ringing that that looks like I might want to use a double angle formulae here. So if we recall, when we have sine 2 theta, this is the same as 2 sine theta cos theta. Now, in my example, I don't have a theta in there, but I've got an 8x. So let's replace theta with 8x here. And if I do that on the left-hand side, that would be sine 16x, okay? 2 times 8x. So we know that sine 16x is the same as 2 sine 8x cos 8x. But we don't have 2 sine 8x cos 8x, we have 4 sine 8x cos 8x. So we have double this. So it won't be 16x, it will be 2 sine 16x. So what I'm going to do now is I'm going to replace 4 sine 8x cos 8x with 2 sine 16x. This is what I'm going to integrate. So what I've now got is a much simpler problem to solve. So when I integrate sine 16x, I'm going to write down here cos 16x. But when we integrate sine, it goes to negative cosine. And also, because I'm integrating, I'm going to need to divide by that coefficient of x here. So divide by the 16. 2 divided by 16 is going to be 1 over 8. And remember, I need to have it as a minus now, because when I integrate sine, it goes to negative cosine. And, of course, last but not least, there is one more important thing here, and that is our plus c. Right, we are 5 problems down with just 1 to go now. So we're going to now look at our question 6, and this is probably going to be by far the longest one. Now in this problem, we might look to do what we did in problem 4 at first, and see, well, if I differentiate my denominator, do I get what's on my numerator? And it looks promising when we differentiate the 4x squared and get 8x. However, when we differentiate minus 25, that's going to go to 0. So we're not going to get a constant term when we differentiate our denominator. So we can't do this by recognition. There's nothing jumps out at us that we can cancel some factors. So really the route I want to go down then is partial fractions. Okay, so I'm going to split this up into 2 fractions that can be easily differentiated. Now, before we split them up, what we need to notice first is that our denominator is just in the form x squared minus a squared. So I can use difference of two squares to factorize my denominator. So just remember, whenever you see this or something like this, we can use difference of two squares. So that will come up throughout your A-level exams quite a lot, and that helpful trick can help you factorize things, and it will allow you to kind of progress with certain questions a little bit further. Now, in this question, I'm going to start by factorizing 4x squared minus 25. So it's still in that form x squared minus a squared, but instead of x squared, we've got 4x squared. So that's going to be 2x. Okay, 2x in both of the brackets there. 2x times 2x makes 4x squared. And 5 squared is 25. So I need to have a minus 5 and a plus 5. Okay, and now I'm going to set this up as partial fractions. So I want this to be in the form some constant that I'm going to call a over 2x minus 5 plus b, which is another constant, over 2x plus 5. And this is just going to make it a lot simpler to integrate with these two simpler fractions to integrate as a result of it. So now what I need to do is find, well, what are those constants a and b? So to do that, I'm going to multiply both sides by 2x minus 5 times 2x plus 5. So when I do that to the left-hand side, the 2x minus 5 and the 2x plus 5 will cancel. And when I times the right-hand side by 2x minus 5 times 2x plus 5, for the first term on the right, the 2x minus 5s are going to cancel. So that will leave me with the 2x plus 5. And for the second term, when you times that by 2x minus 5 times 2x plus 5, it's the 2x plus 5s that are going to cancel, and you get left with the 2x minus 5. Okay, brilliant. So now what we're going to do is we're going to make a substitution here. There are other ways you can do this. You can equate coefficients if you prefer, but I'm just going to do this by substitution. So I'm going to say, let x be minus 5 over 2. Now, why am I choosing minus 5 over 2? Well, that's because when I substitute it into 2x plus 5, then to that bracket there, that's just going to go to 0. 2 times minus 5 over 2 plus 5 equals 0. So that's going to eliminate the a, and that's just going to allow me to find what the value of b is. So let's go ahead and do this. When I substitute in x equals minus 5 over 2, on the left-hand side, when I do that, I do 8 times minus 5 over 2. That's going to be minus 20, plus the 5 for minus 15. When I substitute in x equals minus 5 over 2 into the first bracket, that's going to go to 0. And for the second bracket, when I substitute in x equals minus 5 over 2, what I'm going to get is minus 10. So minus 15 equals minus 10b. Divide both sides by minus 10. And we get a positive 3 over 2. So I found b, now I'm going to find a. And I can do that by substituting x equals positive 5 over 2. And what's going to happen there is that the second bracket will go to 0, and that will allow me to find a. So we substitute in 5 over 2 on the left-hand side, and let's make a little division there. So we substitute 5 over 2 on the left-hand side, and we get 25 when we do that. And then when I substitute it in on the right-hand side, well, in that first bracket, I do 2 times 5 over 2 plus 5, which will give me 10, and then times it by the a. And as we discussed, the second bracket is going to go to 0. So divide through by 10, and we get a as 5 over 2. So now what we can do is we can go back to our problem. And now we know the values of a and b. Rather than integrate 8x plus 5 over 4x squared minus 25, let's think of it as 5 over 2 times 2x minus 5. Okay, what I'm doing there is just substituting in that constant that I found, that a is 5 over 2. You can even just have, you can have it on top of the fraction, but I'm just going to write it as 5 on our numerator and then 2 on the denominator. And then b was 3 over 2, so when we substitute that in, it's going to look like this. And this is what I want to integrate. So looking at the first fraction. Now, if we just ignore the constant for a second and we just thought of this as 1 over 2x minus 5, I'd want to try natural log of 2x minus 5. But as we learned earlier, if we differentiate natural log of a function, what happens is we put the function in the modulus there on our denominator, and we put the derivative of that, which in this case would be 2, on the top. So if you differentiate natural log of 2x minus 5, you get 2 over 2x minus 5. So what we'd have to do then is we'd have to times that by a half so that we can get 1 on the top there. But we don't have 1 on the top here. We have 5 over 2 on the top. So we're going to times by a half, basically the 1 over the coefficient of what's front of the x, and then we're just going to times by our constant that we've got there already, so the 5 over 2. So we're going to do 5 over 2 times a half, so that's going to give us 5 over 4. On to the next one. Yeah, again, I'm going to write there natural log of 2x plus 5. And if I differentiate that back, I would get 2 on the top, 2x plus 5 on the bottom. So imagine it was just 1 over 2x plus 5. I'd have to times this by a half. But because we don't just have a 1 on the top, we've got 3 over 2, essentially on the top, or 3 on the top, 2 on the bottom there. So I'm going to have times 3 over 2 by 1 over 2. So it'll be 3 over 4. And then finally, we have the plus c. So let me know how you got on. Are there any questions that you wanted a little bit more explanation on, or any questions you'd like to see more of, or things that weren't here that you'd like to see? Just let me know how you get on. And yeah, good luck with some more calculus.